Our galaxy is racing through space at over 600 kilometers every second. Something out there in the darkness is pulling us, and everything near us, with unimaginable force. For decades, this cosmic tug has been one of astronomy's greatest puzzles, centered on a hidden monster we call the Great Attractor. It sits in a region of space our telescopes cannot easily see, a gravitational anomaly so vast it dictates the motion of over 100,000 galaxies. By the end of this journey, you will know the 30 deepest secrets of this enigmatic force and the colossal structures that shape our corner of the universe. We will uncover what lies in the forbidden zone that hides it, why most of its mass is completely invisible, and how it is part of a web so large it challenges our understanding of reality itself. What does it feel like to live inside a mystery we are still learning how to see? The first true secret emerged not from a single moment of clarity, but from a slow, meticulous gathering of evidence that began to rewrite the cosmic map. In the 1970s and 80s, a team of 7 astronomers, later nicknamed the Seven Samurai, made a series of careful observations that would shake the foundations of cosmology. They were not looking for a hidden attractor, at least not at first. Their goal was to measure the true motion of our own galaxy and its neighbors, a collection called the local group. To do this, they needed a fixed reference point, a stationary backdrop against which to gauge our speed. They found it in the oldest light in the universe, the cosmic microwave background radiation. This faint glow is the remnant echo of the Big Bang, and it fills all of space uniformly. By measuring tiny, subtle variations in the temperature of this background radiation from different directions, the team could detect our motion through it. Think of it like standing in a gentle, uniform rain. If you are perfectly still, the raindrops hit you evenly from all sides. But if you start running, you will feel more drops hitting your front than your back. The cosmic microwave background is that universal rain, and by feeling which direction it seems warmer, astronomers could calculate our direction and speed. What they found was astonishing. Our entire local group, along with a vast swath of other galaxies, was not drifting randomly. It was racing with purpose, moving at over 600 kilometers per second toward a specific, mysterious point in the distant sky, deep in the constellation of Centaurus. This was our peculiar velocity, a motion above and beyond the general expansion of the universe. The sheer scale of this drift was the first major puzzle. Based on all the galaxies and stars we could see in that direction, the gravitational pull simply did not add up. The visible mass was far too small to account for such a powerful, coordinated tug on millions of galaxies. It was as if every car on a highway was being pulled by an invisible locomotive, one that left no light on the tracks. This velocity anomaly was the first undeniable clue that something monumental was hidden in the shadows, a gravitational secret so profound it would take decades to even begin to understand its true nature. That mysterious point of convergence deep in Centaurus was not just a random spot on the celestial map. It lay directly behind the most impenetrable wall our astronomy has ever faced, a region astronomers call the zone of avoidance. This is the second secret, the reason the Great Attractor remained a ghost for so long. Its precise coordinates are buried in the thick, dusty plain of our own Milky Way galaxy. We are trying to see a distant mountain range, but we are standing in the middle of a dense, glowing forest. The core of our own galaxy, with its brilliant stars, colossal clouds of gas, and immense lanes of interstellar dust, sits directly in our line of sight, completely obscuring the view. For traditional optical telescopes, this zone is a permanent blind spot, a swath of sky where visible light from beyond is simply absorbed or scattered into a meaningless blur. The Great Attractor was not just far away, it was perfectly camouflaged, a literal hidden monster lurking in our own cosmic backyard. This presented an enormous challenge. How do you study something you cannot see? The answer required a shift in perception, moving beyond the light our eyes can detect. To peer through that galactic fog, astronomers had to turn to other wavelengths. Infrared telescopes could sense the heat glow of stars and galaxies shining through the cooler dust, much like night vision goggles can see a person's body heat through a thin veil. Even more powerful were radio telescopes, which could detect the faint whispers of hydrogen gas, the primary building block of galaxies, as it emits a specific radio frequency. By mapping the distribution and motion of this invisible hydrogen, astronomers could begin to trace the shapes and masses of entire galaxies hidden behind the dust, slowly sketching the outline of the monster by its shadow. This was detective work of the highest order, piecing together a portrait of the unseen from indirect clues, a testament to human ingenuity staring into a void and refusing to accept it was empty. The true nature of the monster pulling us was the third and perhaps most humbling secret. The Great Attractor is not a single titanic object. It is not a supermassive black hole of impossible size, nor is it a lone, brilliant galaxy. It is something far more diffuse and yet infinitely more grand. It is a gravitational anomaly, a colossal overdensity of mass, the dense heart of the largest structure we have ever called home. This hidden core is the very center of the Laniakea Supercluster, a name from Hawaiian meaning immeasurable heaven. Laniakea is our home supercluster, a vast web-like filament containing over 100,000 galaxies, including our own Milky Way. Picture a colossal, slow-motion river system flowing across the universe. Individual galaxies are like leaves caught in the current, and these currents all stream toward the deepest gravitational valleys. The Great Attractor is the central basin, the lowest point in the local cosmic landscape where all these galactic rivers converge. It is the focal point, the place where the collective gravity of an unimaginable amount of matter, spread across millions of light years, finally reaches its peak. We are not being pulled by a single hand, but by the accumulated weight of an entire continent of galaxies, all sliding down the slopes of space-time toward a common destination. This realization reframed the entire mystery. We were not looking for a hidden beast, but for the heart of a hidden continent, a place where the fabric of the cosmos itself has been gathered and warped by the sheer concentration of everything around it. So if it is the core of a supercluster, what could possibly lie beyond its pull, shaping its own immense gravity? But the heart of a continent is not empty. At the very core of the Great Attractor's immense gravitational well lies a specific, dense knot of reality known as the Norma Cluster. This is the fourth secret, the visible anchor of the invisible force. Officially catalogued as Able Cluster 3627, the Norma Cluster is a rich, massive gathering of hundreds of galaxies, all bound together in a furious gravitational dance. It is the central marketplace of Laniakea, the bustling, crowded city at the confluence of all those cosmic rivers. The cluster is dominated by a giant elliptical galaxy at its center, a behemoth that has likely grown by consuming its neighbors over billions of years. But the true weight of the Norma Cluster is not just in its stars. The space between its galaxies is filled with an immense cloud of superheated gas, so hot it glows not in visible light but in powerful X-rays. This intergalactic plasma is a seething ocean, heated to millions of degrees by the sheer violence of galaxies moving at tremendous speeds through the cluster's core. This gas represents a staggering amount of mass, far more than all the stars in all the cluster's galaxies combined. When astronomers finally managed to peer through the zone of avoidance with X-ray telescopes, they saw this brilliant, diffuse glow, confirming the presence of a truly massive object. The Norma Cluster is without a doubt the single most significant contributor to the Great Attractor's pull that we can directly observe. Its gravity is a powerful hand tugging on our local group. Yet here lies the ongoing mystery. Even when we add up the combined mass of every galaxy, every star, and every wisp of that scorching gas in the Norma Cluster, the numbers still fall short. It accounts for a large portion of the pull, but not all of it. The monster has a beating heart we can see, but the body of the monster is still hidden in the dark. So what supplies the rest of the gravitational force? What unseen mass is woven into the fabric of this region, completing the picture of the attractor? The fifth secret revealed that the monster has a monster of its own. For decades, astronomers focused on the Great Attractor as the ultimate source of our motion, the final destination. But as our maps of the distant universe improved, a far larger player emerged from the shadows, located even deeper in the constellation of Centaurus. This is the Shapley Supercluster, the single most massive concentration of galaxies we have ever identified in the observable universe. To grasp its scale, consider our home, the Laniakea Supercluster. It is a sprawling continent of 100,000 galaxies. The Shapley Supercluster is a continent on steroids, a dense, overwhelming knot of matter containing perhaps 300,000 galaxies, all packed into a region of space that defies comprehension. Its gravitational influence is so profound it warps the very flow of galaxies across hundreds of millions of light-years. And here is the pivotal realization that reshaped the entire cosmic tug-of-war. We are not being pulled solely toward the Great Attractor. We, along with the Great Attractor itself, are being pulled toward Shapley. Picture a vast, slow-motion river. Our local group is a leaf floating downstream toward a powerful whirlpool, the Great Attractor. But that entire river system, whirlpool and all, is itself flowing toward a colossal, distant waterfall, the Shapley Supercluster. The motion we detected, that 600 km/s rush, is the combined pull of both of these titanic structures. The Great Attractor is not the end of the line, it is a major waypoint on a far grander journey. This discovery added a crucial layer to the mystery of large-scale flows. It showed that gravity's reach is not limited to our immediate neighborhood. It creates chains of influence that cascade across the cosmos, with smaller attractors falling into larger ones in an endless hierarchy. So if our motion is a sum of these two immense pulls, what happens when we try to subtract one from the other? What does that tell us about the true, hidden mass of the Great Attractor itself? That missing mass, the invisible component completing the gravitational equation, points us toward the sixth and perhaps most fundamental secret. Over 90% of the Great Attractor's immense pull comes from a substance we cannot see, touch, or even directly detect. It is the ghost in the cosmic machine, dark matter. This is not a small ingredient, it is the overwhelming majority of the substance that shapes our universe. The Great Attractor, in all its hidden grandeur, is not primarily a structure of stars and gas. It is a colossal monument built by dark matter, with galaxies like ours merely tracing its outline like glitter sprinkled on wet paint. We know it is there because of what it does. The visible components, the galaxies and the hot gas of the Norma Cluster, are moving with speeds that would send them flying apart if only their own gravity were holding them together. They are orbiting an invisible center of mass, held in place by the gravitational grip of something far more massive than anything we can photograph. Think of it like watching leaves swirling in a powerful, unseen whirlpool. You cannot see the water's current, but the frantic, coordinated motion of the leaves tells you exactly where the vortex is and how strong its pull must be. Astronomers measure the speeds of galaxies streaming toward the attractor and the velocities of galaxies within clusters like Norma. These motions, these galactic orbits, are the leaves in the whirlpool. By applying the laws of gravity, they can calculate exactly how much mass must be present to create those observed speeds. The answer is always the same. The required mass is about 10 times greater than everything luminous we can tally. This makes the Great Attractor one of the most significant natural laboratories we have for studying dark matter's behavior on a truly epic scale. Its gravitational well is so deep and complex that it allows scientists to map how this invisible scaffolding is distributed. Does it form an even, diffuse cloud, or does it clump in specific ways, creating dense knots and filaments that guide the placement of galaxies? The flows of galaxies toward the attractor are like cosmic wind veins, pointing toward the densest concentrations of this dark material. By charting these flows in 3 dimensions, we are essentially drawing a map of the dark matter landscape, revealing the hidden skeleton upon which the glittering galaxies are hung. So if dark matter forms this invisible skeleton, what is the visible flesh of the universe doing? How do galaxies actually move within this dark framework? Galaxies do not just fall toward dense attractors, they are also pushed away from emptiness. This is the 7th secret, a revelation that our motion is shaped as much by what is missing as by what is present. While we race toward the immense concentrations of mass in the Great Attractor and the Shapley Supercluster, something equally powerful operates from the opposite direction. Astronomers call it the dipole repeller. Imagine you are in a boat on a wide, calm lake. If you dig a massive hole in the water on one side of the boat, the water will rush in to fill that emptiness. Your boat is not pulled toward the hole by a force, but it is pushed from behind because the water level behind you is now higher. The dipole repeller is that cosmic hole. It is a staggering void, an underdense region of space spanning hundreds of millions of light years where the distribution of galaxies is far, far below the cosmic average. This void does not exert an active repulsive force. Nothing in gravity does that. Instead, it creates a relative push because its gravitational pull is so weak. The average density of the universe tugs on us from all sides, but in the direction of the dipole repeller, that tug is significantly weaker. The stronger pull from the overdense regions in the opposite direction, like the Great Attractor, now meets less resistance. We are effectively sliding down a hill with the peak behind us eroded away. Our journey is not a simple freefall toward a single point. We are caught in a grand cosmic imbalance, squeezed between the immense pull of hidden mass in one direction and the startling absence of it in the other. This understanding transforms the Great Attractor from a lone monster into one half of a vast dynamic system. Our home is not just being dragged, it is being flushed along a channel carved by both presence and absence on a scale the human mind can barely grasp. The dust that blinded our optical view was not an absolute barrier, it was a filter. To see the structure hidden within the Great Attractor, astronomers had to learn to see the heat of the universe itself. This was the breakthrough of the 8th secret, a project that turned our obscured backyard into a detailed map. The 2-micron all-sky survey, known as 2MASS, was a monumental effort that scanned the entire heavens in infrared light. Infrared radiation has a longer wavelength than visible light, allowing it to pass through interstellar dust clouds with far less scattering, much like the heat from a fireplace can warm you through a foggy window. 2MASS did not look for the brilliant blue light of young stars or the vivid glow of nebulae. Instead, it patiently recorded the subtle, warm infrared glow emitted by the older, cooler stars that make up the bulk of a galaxy's mass. This was the key. By mapping this pervasive stellar heat, the survey could detect entire galaxies whose visible light was completely extinguished by the Milky Way's dusty plain. The zone of avoidance, once a blank spot on the cosmic chart, began to fill with thousands of faint red dots, each one a previously hidden galaxy. The resulting map was transformative. It did not just show a few extra galaxies near the attractor, it revealed the full, sprawling architecture of the mass concentration. The Great Attractor was no longer a vague, theoretical point of convergence. 2MASS showed it as the dense core of a vast, interconnected network, with filaments of galaxies streaming into it from all directions, confirming its role as the gravitational heart of the Laniakea Supercluster. The survey painted the attractor not as a solitary monster, but as the central hub of a colossal, spinning wheel, with our own Milky Way located out on one of its faint, spiral arms. This infrared sensors provided the first comprehensive inventory of the visible mass in that forbidden zone, allowing scientists to finally weigh the stellar component of the anomaly with precision. Yet, even with this clearer picture, the same old gravitational math persisted. The added galaxies from 2 mass accounted for more mass, but still not enough. The map showed where the glitter was sprinkled, but the true weight of the canvas beneath it remained invisible. If infrared could reveal the hidden galaxies, what tool could possibly reveal the empty spaces between them, the voids that shape the cosmic landscape just as powerfully? The universe's hidden architecture glows with a light our eyes can never see. To map the deepest gravitational wells of the Great Attractor, astronomers needed a form of vision that could perceive energy 1,000,000 times more powerful than visible light. They turned to X-rays. In the early 1990s, a groundbreaking observatory named ROSAT was launched. Its instruments designed not to look at stars, but to scan the sky for the searing signatures of extreme violence and unimaginable heat. When it pointed toward the obscured region of Centaurus, it did not see darkness. It saw a blazing, diffuse fire. ROSAT discovered that the space between galaxies in clusters like Norma is not empty. It is filled with a vast ocean of superheated gas known as the intracluster medium. This gas is so incredibly hot, heated to tens of millions of degrees, that it does not glow in any color we recognize. Instead, it emits high-energy X-rays, a fierce radiation born of pure thermal chaos. Think of it like this: if you could see the Great Attractor region with X-ray eyes, the galaxies themselves would appear as faint, cool dots. The true spectacle would be the colossal, shimmering clouds of plasma that engulf them, glowing with the intensity of 1,000,000,000 invisible suns. This discovery was a revelation. That hot gas is a direct tracer of gravity's deepest pits. For gas to become that hot, it must have fallen into an immensely powerful gravitational well, gaining tremendous speed and colliding with other infalling material, converting that motion into raw heat. The sheer amount of this glowing plasma allowed scientists to make a critical measurement. They could weigh it, and the weight was staggering, often exceeding the combined mass of all the stars in all the cluster's galaxies. ROSAT's maps confirmed that the Great Attractor's core was not just a collection of galaxies. It was a cauldron of primordial matter, held and heated by a gravitational grip far stronger than the visible components could provide. This was the 9th secret, written in the fiery script of X-rays. The hidden mass was not just dark, it was also blisteringly hot and luminous in a way we had only just learned to perceive. But even this was just a first glimpse. A newer, far more powerful eye has now opened, promising to see this hidden fire in greater detail than ever before. The faintest light in the universe carries the imprint of our entire journey. That ancient glow from the Big Bang, the cosmic microwave background, is not perfectly uniform. It holds a subtle, telltale pattern known as the dipole anisotropy, and it is the most elegant proof we have of our race toward the hidden monster. This temperature difference is incredibly slight, a variation of just a few thousandths of a degree. But its meaning is profound. In the direction of the Great Attractor, the CMB appears ever so slightly warmer. In the exact opposite direction, toward the dipole repeller, it appears a tiny bit cooler. This is not a feature of the early universe, it is a signature of our own motion, a cosmic speedometer written in heat. The cause is the Doppler effect, the same phenomenon that makes a siren's pitch rise as it approaches you and fall as it moves away. We are plowing through the sea of microwave radiation at over 600 kilometers per second. The photons hitting us head-on from the direction we are moving are compressed, shifting their energy slightly higher, which we perceive as a minuscule increase in temperature. The photons from behind us are stretched, their energy lowered, making that part of the sky seem cooler. This independent measurement, taken from the edge of time itself, confirms the velocity first detected by the 7 samurai. It tells us that our entire local frame of reference, everything bound to us by gravity, is in concerted motion. We are not just observing the Great Attractor from a distance, we are actively falling toward it, and the oldest light in existence bears the mark of that fall. Our cosmic address was rewritten in 2014, and the new map revealed a home far vaster than we ever knew. This was the discovery of the Laniakea Supercluster, a structure so immense its name means immeasurable heaven in Hawaiian. Before this, we thought our local group of galaxies belonged to a structure called the Virgo Supercluster, named for the dense Virgo cluster at its heart. But new data showed that was only a small part of the story. A team of cosmographers led by Brent Tully and Helene Courtois performed a monumental feat of cosmic cartography. They did not just map where galaxies are, they mapped how they move. By measuring the precise velocities of thousands of galaxies relative to the universe's expansion, they could trace the subtle flows of gravity, the way water flows downhill across a continent. They were mapping watersheds in space. Every galaxy, they realized, is flowing along a specific path toward a common gravitational basin, just as every raindrop in a given valley flows toward the same river and eventually the same sea. The boundaries of a supercluster, they defined, are not where galaxies stop, but where their flows diverge toward a different ultimate destination. When they drew these boundaries based on the motion of galaxies, the true scale of our home emerged. Laniakea spans over 500 million light-years and contains roughly 100,000 galaxies, all streaming along vast filamentary highways toward a single, deep gravitational valley. And at the very bottom of that valley, at the focal point where all those galactic rivers converge, sits the Great Attractor. It is not a monster lurking in the dark, it is the beating heart of our home continent. Our own Milky Way, with all its hundreds of billions of stars, is not anywhere near the center. We are out on the distant, sparse fringes of Laniakea, like a remote island in a vast archipelago, slowly but surely following the current toward that hidden core. This redefinition was humbling and clarifying. It framed the Great Attractor not as an external mystery, but as the central feature of our own cosmic neighborhood, the gravitational anchor around which our entire local universe slowly turns. The heart of our continent is also on a journey. The Great Attractor, for all its immense gravitational power, is not a fixed point in space. It is itself in motion, caught in a flow far greater than its own. This is the 12th secret, a cascade of cosmic movement that stretches across the observable universe. We are falling toward the attractor, but the attractor is also falling. Its ultimate destination lies even deeper in the constellation of Centaurus, in the overwhelming gravitational embrace of the Shapley Supercluster. This creates a staggering hierarchy of motion, a cosmic Russian nesting doll of influence. Our local group flows toward the Great Attractor. The Great Attractor flows toward Shapley, and entire collections of superclusters may be flowing toward something even more immense beyond our current view. This coordinated movement of matter on the very largest scales is what astronomers call a bulk flow. Picture a vast, slow-motion river system spanning billions of light-years. Individual galaxies are like leaves, but they are not drifting independently. They are caught in colossal currents that move entire superclusters together, as if the fabric of space itself has a gentle continental tilt. The Great Attractor sits in one of the deepest parts of this river, but it is not the source of the current. It is a massive whirlpool within the greater stream, both shaping the local flow and being carried along by it. Measuring these bulk flows is one of the most delicate tasks in cosmology. It requires subtracting the uniform expansion of the universe, then subtracting the local pulls from nearby structures to see what underlying motion remains. The persistent drift that points toward Shapley tells us that the distribution of mass in the universe is not even on the grandest scales. There are still imbalances, vast overdensities and underdensities that set entire continents of galaxies in motion relative to the cosmic background. So if we are all caught in these rivers, where do they begin? What is the source of the tilt that sets 100,000 galaxies adrift? The map of our cosmic neighborhood just became far more crowded. For years, the Great Attractor and the Shapley Supercluster dominated our understanding of the mass pulling us, but they were not the only giants hiding in the galactic shadows. In 2016, astronomers announced the discovery of another colossal structure, one that had been perfectly camouflaged behind the same veil of dust and stars. This is the Vela Supercluster, a sprawling network of galaxies so vast it challenges our picture of what lurks in the so-called zone of avoidance. Its detection was a triumph of patient, multi-wavelength observation, piecing together clues from galaxy surveys that could peer through the Milky Way's dusty plain. The initial hints came from counting galaxies detected in infrared and radio surveys, revealing an unexpected overdensity, a suspiciously high number of galaxy counts in a region that was supposed to be obscured. Follow-up measurements of their distances confirmed the terrifying scale. This was not a small group or a lone cluster. It was a supercluster in its own right, potentially containing several massive clusters of galaxies and spanning hundreds of millions of light years. Its location is deeply significant. It sits in the general direction of the Great Attractor, overlapping the same mysterious sector of sky. This suggests a startling possibility that the Great Attractor is not a solitary gravitational pit, but perhaps just one node in an even larger, interconnected complex of mass, a cosmic megalopolis where the Vela Supercluster and the core of Laniakea are gravitationally entwined. Think of it like discovering a hidden mountain range right next to a known massive peak. The two are part of the same continental root structure, pulling on the landscape together. The discovery of Vela forces a profound recalculation. The total mass tugging on our local group and on the Great Attractor itself may be distributed across an even wider and more complicated landscape than our best models assumed. It means the zone of avoidance is not just hiding one secret, it is hiding an entire tapestry of them, woven together by gravity into a single, overwhelming force. If such a behemoth could stay hidden for so long, what other structures might still be lurking, unseen, in the dark folds of our own galaxy? Computer simulations have given us a time machine to witness the birth of giants. To understand how a structure as vast and complex as the Great Attractor could form, scientists turn to the most powerful supercomputers on Earth, running programs that simulate the evolution of the entire universe. The most famous of these is the Millennium Simulation, a landmark project that recreated the growth of cosmic structure over 13 billion years. It did not start with galaxies or stars, but with a nearly uniform sea of dark matter, the invisible scaffolding of reality. The simulation then let the simple, relentless force of gravity work across cosmic time. As the virtual universe expanded, tiny quantum fluctuations from the Big Bang, imprinted in the early universe, began to grow. Regions with just a fraction more dark matter exerted a slightly stronger pull, drawing in more material from their surroundings. Over billions of virtual years, this snowball effect transformed a smooth, cloudy haze into an intricate three-dimensional web. The results are breathtaking visual maps that look like the neurons of a cosmic brain. Vast, thread-like filaments of dark matter stretch across unimaginable voids, intersecting at dense, tangled knots. These knots are the nodes of the cosmic web, the natural anchors for the superclusters we observe. The Great Attractor is not an anomaly in this simulated view, it is an expected feature. It is precisely the kind of massive node that forms where several of the universe's largest filaments cross. In the simulation, you can watch rivers of dark matter flow along these filaments for billions of light years, funneling an immense amount of mass into these central junctions. The visible galaxies we see are merely the trace elements, the bits of ordinary matter that cooled and collapsed within these pre-existing dark matter wells. This virtual universe tells a compelling story that the Laniakea Supercluster and its Great Attractor heart are not random accidents. They are the inevitable consequence of gravity amplifying the faintest whispers from the dawn of time, weaving a web whose strongest threads were destined to meet. The faint echoes of creation give us a ruler to measure the cosmos. Long before the first stars flickered on, the universe was a seething, opaque plasma, a hot soup of particles and light. In that primordial fury, sound waves raced outward from every density fluctuation, compressing and rarefying the hot gas in spherical shells. These were not sound waves as we know them, but pressure waves moving at a significant fraction of light speed through the early universe's dense fluid. Then, roughly 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely in what we call the cosmic microwave background. At that moment of release, those traveling sound waves were frozen in place, imprinting a subtle, preferred scale onto the distribution of matter. This fossilized imprint is what we call a baryon acoustic oscillation. It left a signature in the CMB, a statistical preference for hot and cold spots to be separated by a specific angular distance on the sky. More importantly for our story, it also imprinted that same scale into the distribution of the matter that would later collapse into galaxies. Think of it like tossing a handful of pebbles into a still pond. Each pebble creates an expanding ring of ripples. If you freeze the pond the instant the ripples reach a certain size, every ring will have the same radius. In the universe, each initial density peak was like a pebble, and the frozen sound wave is that standard ring. This gives cosmologists a gift of unimaginable value, a standard ruler etched into the fabric of space itself. We know the physical size of that frozen sound wave, about 500 million light-years across, because we can calculate the speed of sound in the early universe and the time it had to travel before the universe became transparent. This knowledge transforms how we map the large-scale structure containing the Great Attractor. When astronomers conduct massive galaxy surveys, they do not just plot where galaxies are. They look for a statistical excess of galaxy pairs separated by that specific 500 million light-year scale. It is a subtle signal, like hearing a faint, recurring note in a cosmic symphony, but it is unmistakable. By finding this preferred separation in the galaxy distribution around us, we can measure how the universe has stretched over time. We can see if structures in the direction of the Great Attractor appear compressed or expanded relative to this ruler, telling us about the local flow of matter and the strength of gravitational pulls. This technique provides an independent, powerful check on the mass distribution that creates attractors and voids. It confirms that the colossal flows we see, the motion toward the Great Attractor and away from the dipole repeller, are consistent with the underlying dark matter skeleton mapped by this ancient, echoing ruler. The monster's shadow is measured by the echoes of its birth. Even the ordinary matter in the Great Attractor is playing a cosmic game of hide and seek. We can feel its immense gravity, and we have mapped many of its galaxies and hot gas clouds, but a troubling accounting problem remains. When scientists add up all the normal or baryonic matter they can detect in that region, the stars, the glowing gas, the dust, a significant portion is simply missing. This is not the dark matter mystery, this is something else. This is the mystery of the missing baryons, and it points to a hidden component of the universe's most basic building blocks. According to our best models of the Big Bang, there is a specific predicted amount of ordinary matter, protons and neutrons, that should exist in the universe today. Observations of the very early universe from the cosmic microwave background confirm this number with exquisite precision. Yet, when we look around at the present-day universe and tally everything we can see, we come up short by about half. A staggering 50% of the ordinary matter that must exist is not in galaxies or in the hot gas of clusters. So where did it go? The leading hypothesis is that it is hiding in the cosmic filaments themselves, the vast threads of the web that connect great clusters like the Norma Cluster to the rest of the universe. Theorists call this the warm-hot intergalactic medium, or WHIM. It is a ghostly, diffuse gas spread so thin that a cubic meter of it might contain only a single atom. But it is also incredibly hot, heated to hundreds of thousands or even millions of degrees as it was funneled into the filaments by gravity's pull. This combination makes it fiendishly difficult to detect. It is too hot to glow in visible light and too thin to emit strong, concentrated X-rays like the dense gas in a cluster core. Finding it is like trying to spot a wisp of steam in a darkened room using only a faint flashlight. Astronomers have had to become detectives of the faintest possible signals. They look for distant, brilliant objects like quasars, whose light passes through billions of light years of space on its way to us. As that light pierces the cosmic web, atoms in the WHIM can absorb specific telltale wavelengths, leaving ultra-faint fingerprints in the quasar's spectrum. It is painstaking work, but these absorption lines have begun to confirm that the missing matter is indeed there, woven into the fabric of the filaments. In the context of the Great Attractor, this means a substantial part of its gravitational pull from normal matter comes not from its brilliant core, but from these immense, nearly invisible rivers of hot gas that flow into it. The monster is not just fed by galaxies, but by an entire hidden circulatory system of ordinary matter, so diffuse it has eluded us until now. The ultimate fate of the Great Attractor is written in a battle between two fundamental forces, one that binds and one that tears. On the grandest scale, the universe's expansion is accelerating, driven by a mysterious dark energy. Over trillions of years, this acceleration will win the war, stretching the cosmic web so thin that galaxies beyond our immediate neighborhood will fade from view, receding faster than light can bridge the gap. But gravity is a stubborn, local force. Within our own Laniakea Supercluster, the gravitational bonds are simply too strong for dark energy to break. The galaxies within our continent of space, including our Milky Way and the Norma Cluster at the attractor's heart, are bound together for eternity. They will not be flung apart. Instead, their destiny is one of slow, inevitable consolidation. Over the next many billions of years, the streaming flows that define Laniakea will continue. All 100,000 galaxies will complete their long journey into the gravitational basin, merging and coalescing into a single, monstrous elliptical galaxy. This future entity, sometimes called Laniakea Major, will be a behemoth of almost incomprehensible scale, a dark, quiet island of stars in an otherwise empty and expanding void. The Great Attractor will cease to be an attractor because there will be nothing left to attract. It will have become the final, unified core of all that was once our local universe. Yet even this may not be the end of the story. Remember, Laniakea itself is falling. The same gravitational currents that pull us toward the attractor are pulling the attractor toward the even more massive Shapley Supercluster. On a timescale that dwarfs the merger of Laniakea, these two titanic structures may themselves be drawn together. Picture two colossal islands in a darkening sea, slowly drifting toward one another over hundreds of billions of years. Their eventual collision and merger would create a structure of such mass it defies our current vocabulary, a hypercluster that represents the final, grand act of assembly before the accelerating universe isolates it forever. So the Great Attractor is not a permanent fixture, it is a phase. It is the gathering point for our local cosmos, a temporary focal point in an endless dance where gravity builds empires, only for them to become lonely monuments in an ever-widening emptiness. Our cosmic neighborhood is not just a collection of points, but a tapestry of immense walls. The first of these colossal barriers to be discovered shattered our understanding of how matter could be arranged on the grandest scales, and it emerged from a project with a humble name, the Center for Astrophysics Redshift Survey, or CFA2. In the late 1980s, astronomers Margaret Geller and John Huckrow were meticulously mapping the three-dimensional positions of galaxies by measuring their redshifts. They expected to find a roughly uniform, lumpy distribution, the so-called cosmic foam. What they saw instead when they plotted their data was a structure so vast and unexpected it was promptly dubbed the Great Wall. This was not a dense cluster or a loose filament, but a nearly flat, gargantuan sheet of galaxies, a true wall in space. It stretches over 500 million light-years long, 200 million light-years wide, but is only about 15 million light-years thick. To grasp its shape, picture a single, enormous pane of cosmic glass, thinner than a sheet of paper relative to its length and width, with thousands of galaxies embedded in it like glitter. This CFA2 wall, also called the Coma Wall for the famous Coma Cluster that lies within it, revealed a startling truth. The universe's large-scale structure was not just clumpy, it could organize into coherent, flattened formations of staggering size, structures that seemed to defy the notion of a smooth and random cosmos. It was a foundational discovery, proving that gravity could weave matter into patterns far grander than anyone had dared to predict. But if that wall seemed immense, it was merely a prelude to an even more staggering revelation. The true scale of cosmic architecture would be revealed by a survey that dwarfed all previous efforts. The Sloan Digital Sky Survey, beginning in 2000, used a dedicated telescope to systematically image and map millions of galaxies across a vast swath of the sky. Its digital eye peered deeper and wider than ever before, and in 2003 it unveiled a structure that holds the record to this day, the Sloan Great Wall. This is not a simple, flat sheet like its predecessor. It is a colossal filament, a sinuous, interconnected network of galaxy clusters and groups that forms a dense, elongated ribbon across the cosmos. Its scale is almost incomprehensible, spanning approximately 1.37 billion light-years in length. To put that in perspective, a beam of light, the fastest thing in the universe, would need over 1,300 million years just to travel from one end of this structure to the other. It contains thousands upon thousands of galaxies, all gravitationally linked in a single, meandering chain that makes our own Laniakea Supercluster look like a modest suburb. The Sloan Great Wall represents the ultimate expression of the cosmic web's filamentary nature, a backbone of the universe so large it arguably challenges the cosmological principle itself, the idea that on the largest scales, the universe should look roughly the same in every direction. The contrast in their discovery tells a story of technological evolution. The CFA2 wall was found through painstaking, targeted observations of specific slices of the sky, a masterpiece of analog-era cosmology. The Sloan Wall was a product of the digital age, an automated, sweeping census that allowed patterns to emerge from an ocean of data. Both structures, however, whisper the same profound secret. Gravity's work is not finished with making galaxies and clusters. It is an artist sculpting continents and mountain ranges on a canvas billions of light-years across, and we are only beginning to see the full outline of its masterpiece. The universe saves its most extreme contradictions for the darkest corners of the map. While immense walls of galaxies trace the dense threads of the cosmic web, the voids between them can grow so vast they become terrifying in their emptiness. Two structures discovered in the last 2 decades represent the ultimate expression of this cosmic duality, one a wall of staggering scale, the other a void of haunting nothingness. The first is known as the Hercules Corona Borealis Great Wall. Detected in 2013 by mapping gamma-ray bursts, the most violent explosions in the universe, this structure is a contender for the largest single formation we have ever identified. Its scale is difficult to even articulate. It spans an estimated 10 billion light-years in its longest dimension. To put that number in perspective, the entire observable universe is only about 93 billion light-years across. This single wall of galaxies, a filament of clustered gamma-ray burst sources, occupies roughly 10% of the observable diameter of everything that exists. Its discovery sent shockwaves through cosmology because its sheer size appears to violate a fundamental rule known as the cosmological principle. which states that the universe should look roughly the same in every direction when viewed on a sufficiently large scale. A structure 10 billion light-years long is not just a large feature, it is a potential crack in the foundation of our models, suggesting that matter may be distributed in patterns far more uneven and coherent than we ever thought possible. The Wall's discovery method itself is a secret of modern astronomy. We cannot see its individual galaxies at such immense distances, but we can see the brilliant, fleeting flashes of gamma-ray bursts that occur within them. These catastrophic events, marking the deaths of massive stars or the collisions of neutron stars, serve as brilliant beacons, pinpricks of light that outline the hidden architecture of the distant cosmos. Mapping their positions revealed this inconceivable concentration, a backbone of the universe so grand it seems to define an entire sector of space. If such a wall truly exists at that scale, it forces us to ask if our universe is more textured, more patterned, and perhaps more strangely ordered than our theories allow. In stark, almost violent contrast to that overwhelming density lies the Boötes void. Discovered much earlier in the 1980s, it presents the opposite cosmic extreme. While the Hercules Corona Borealis Wall is a monument to presence, the Boötes void is a cathedral to absence. It is a spherical region of space roughly 330 million light-years across that contains almost nothing. In a volume of the universe that should hold thousands of galaxies, astronomers have found only about 60, lost in that immense darkness like a handful of lonely ships adrift on an ocean that spans millions of light-years. If our Milky Way were placed at the center of the Boötes void, we would not have known other galaxies existed until the 1960s, when our telescopes finally became powerful enough to peer beyond its terrifying borders. The existence of such a vast emptiness is a profound puzzle. How does gravity, which pulls matter together, leave behind a bubble so large and so empty? The leading theory is one of merging, a process where smaller voids, which are common in the frothy structure of the universe, gradually run into each other over billions of years. Their boundaries merge, their walls of galaxies break and thin, and they combine into a single, monstrous supervoid. Think of soap bubbles on the surface of water, slowly coalescing into one giant, empty sphere. The Boötes void may be the result of such a cosmic consolidation, a place where the expanding emptiness of many regions finally joined into one. Its very existence is crucial to understanding the dynamics of the cosmic web. Voids are not passive holes, they are active drivers of large-scale motion. As they grow, they push matter outward, contributing to the flows that shape superclusters and attractors. The Great Attractor, in part, exists because of the push from voids like the dipole repeller, and the Boötes void represents the ultimate expression of that pushing force. These two structures, the wall of impossible density and the void of shocking emptiness, are not opposites in a fight. They are partners in a dance, the inhale and exhale of the cosmos, defining each other by their very contrast. One shows us how much matter can gather, the other shows us how completely it can retreat, and between their extremes lies the full, dynamic spectrum of our reality. Our maps of the cosmic web keep growing, revealing giants hidden in plain sight. The South Pole Wall is one such leviathan, a colossal filament of galaxies so immense it rivals the Sloan Great Wall, yet it remained unseen until very recently because of where it is located. This vast structure does not lie behind the dusty plain of our galaxy, but in a different kind of blind spot, the southern galactic pole. This region is not obscured by dust, but it is simply an area of the sky that historically received less attention from major northern hemisphere telescopes. It was the shadows cast by this wall that finally gave it away. Astronomers were not looking directly for it, they were studying the peculiar velocities of galaxies, those subtle deviations from the universe's expansion. They noticed a coherent flow, a vast stream of galaxies all moving in the same direction, and that motion pointed toward an unseen source of immense gravity. By tracing these flows backward, like following the wind to find a mountain range, they mapped the gravitational landscape and uncovered the wall. It is a curving sheet of galaxies nearly 1.4 billion light-years long, a backbone of the cosmos that stretches across the southern sky, hidden not behind dust but behind the limits of our own perspective. Its discovery in 2020 was a triumph of modern data synthesis, combining distance measurements from multiple surveys to build a three-dimensional picture of what our eyes could not directly see. This wall is a gravitational anchor on a continental scale, influencing the motion of thousands of galaxies, including our own, in ways we are only beginning to measure. It is a reminder that the universe's largest features are not always where we choose to look, and that our own position can blind us to the architecture just over the horizon. But if the South Pole Wall is a single, immense backbone, there exists an even broader category of structure, a sprawling network that makes a supercluster look like a neighborhood. This is the Pisces-Cetus supercluster complex, a web of interconnected superclusters that forms one of the largest contiguous assemblies of matter in our entire observable universe. The term supercluster complex itself tells a story of escalating scale. We have galaxies which gather into clusters which link into superclusters like Laniakea. The Pisces-Cetus complex is what happens when superclusters themselves are gravitationally intertwined, forming a metastructure of almost unfathomable breadth. It is not a single, dense knot, but a vast sponge-like network of filaments and nodes spanning over 1 billion light-years. Within it, famous superclusters like Pisces-Cetus, the Perseus-Pisces supercluster, and others are not isolated islands but connected provinces in a single, gargantuan continent of galaxies. Mapping something this vast requires a cosmic census of unprecedented scope, the work of projects like the Sloan Digital Sky Survey, which have painstakingly charted the three-dimensional positions of millions of galaxies. These maps, when viewed from a sufficient distance, reveal the gossamer threads of the cosmic web in stunning detail, with the Pisces-Cetus complex standing out as one of its most prominent features. Its discovery and definition are a direct result of our improving three-dimensional cartography of the cosmos. We are no longer just plotting dots on a flat sky. We are building a true atlas of depth and distance, revealing how matter is woven together across the largest possible scales. These two structures, the newly mapped wall and the ancient, sprawling complex, represent the cutting edge of cosmic geography. They show us that the universe is structured like a fractal, with patterns repeating from the scale of galaxy clusters up to these billion light-year formations. Each new layer we uncover forces us to ask, is there a pattern even larger than this? This elegant rule of cosmic uniformity is known as the cosmological principle. It states that on sufficiently large scales, the universe should look essentially the same in every direction and from every location, a concept called homogeneity and isotropy. There is a profound idea tied to this principle, a theoretical threshold known as the end of greatness. It suggests that above a certain scale, roughly 300 million light-years, the grand walls, voids, and filaments should dissolve into a smooth, featureless sea of matter. We should no longer see individual, definable structures, but a uniform statistical distribution, like looking at a vast forest from so high up that the individual trees blur into a single green canopy. This principle is not just philosophical, it is the bedrock upon which our entire model of cosmology is built, from the equations of general relativity to our understanding of the Big Bang. If the universe were not homogeneous on the largest scales, our fundamental measurements of its expansion, its age, and its composition would be thrown into chaos. So when we discover a structure like the Hercules Corona Borealis Great Wall, stretching an alleged 10 billion light-years, it does more than just break a size record. It stares directly at the end of greatness and asks a silent, formidable question. Is this wall real, and if it is, does it break our most fundamental rule? The debate among cosmologists is fierce and fascinating. One camp argues that such an immense filament is not a true, physically connected structure in the way a supercluster is. It could be a chance alignment, a statistical fluke where several independent filaments, lying at different distances along our line of sight, appear connected from our singular vantage point. We are seeing a cosmic mirage, a trick of perspective where separate threads in the tapestry line up to look like a single, impossibly long rope. Our methods of detection also come under scrutiny. Mapping with gamma-ray bursts is powerful, but these events are rare and their distances can have significant margins of error. Could a slight misjudgment in distances create the illusion of a connected wall where none exists? The other camp points to the sheer statistical unlikelihood, the probability of so many gamma-ray bursts, the most violent and rare events we know, aligning by pure chance across 10 billion light-years seems vanishingly small. This wall, they argue, is a real feature, a backbone of the cosmic web so immense it reveals a universe more textured and lumpy than our models predicted. It suggests the end of greatness may lie at a far larger scale than we thought, or that our universe has preferred directions and patterns we do not yet understand. This is not merely an academic dispute, it cuts to the heart of how we see our place in the cosmos. Are we living in a universe that is fundamentally smooth and featureless on the grandest stage, or is it a place of perpetual hierarchy with structures nesting within larger structures, perhaps without end? The answer will not come from a single discovery, but from the next generation of galaxy surveys, mapping billions of galaxies with exquisite precision, finally allowing us to see if the great walls are true continental divides or merely shadows on the cave wall. The architecture of the cosmos is not a random scattering of lights, but a delicate, intricate web. This is the fundamental design of our universe, a structure so vast and elegant it reveals the hidden hand of gravity itself. The cosmic web is built from a scaffold of dark matter, the invisible substance that makes up the bulk of all matter. In the early universe, tiny ripples in the density of this dark matter were amplified by gravity over billions of years. Regions with a slight overdensity pulled in more material from their surroundings, while underdense regions were emptied out. This process did not create a uniform lumpiness, but a specific, beautiful pattern, a network of dense filaments connecting at dense nodes with enormous voids stretching between them. Think of it like watching foam form in a sink. The soapy water arranges itself into a network of thin films, intersecting at junctions with large, empty bubbles trapped inside. The dark matter web is that three-dimensional foam on a cosmic scale, a skeleton woven from gravity alone. It is within the densest strands of this dark matter filament that ordinary matter, the gas and dust that make stars and planets, found its home. As gas flowed along these invisible rivers of gravity, it cooled, condensed, and eventually ignited into the galaxies we see. Galaxies are not scattered randomly. They trace the underlying dark matter architecture like dew on a spider's web, glittering along the strands and clustered at the intersections. The Great Attractor is a perfect example of one of these mighty intersections. It is not an isolated pit, but a colossal node where several of the universe's largest dark matter filaments converge. Imagine a grand central station in an interstellar railway network. Vast tracks, the filaments, stretch across millions of light years, carrying rivers of gas and entire galaxies along their gravitational currents. All these tracks lead to a central hub, a place of immense density and traffic where the flows meet and merge. That hub is the Great Attractor. The Norma Cluster and the other galaxies we detect are simply the visible cargo that has collected at this central junction after traveling the dark matter highways for eons. This filamentary structure explains why we see coherent flows of galaxies, like our own local group, moving with purpose. We are not falling toward a single point in empty space. We are traveling along one of these grand filaments, sliding down a slope in the dark matter landscape toward the deepest valley where the filaments join. The web is dynamic, constantly funneling material toward its nodes, making structures like the attractor grow ever more massive over time. This cosmic architecture turns the universe from a collection of isolated islands into a single, connected continent, with rivers of dark matter defining every mountain, valley, and destination. The universe's expansion gives every galaxy a predictable speed, a clean signature of its distance. But look closer, and that signature is smudged. Galaxies have a second motion, a secret drift superimposed on the grand expansion, and it is this deviation that reveals the true gravitational landscape. Astronomers call this a galaxy's peculiar velocity, and it is the key to mapping invisible forces like the Great Attractor. Think of it like watching leaves floating down a wide, slow river. The river's current is the Hubble expansion carrying every leaf along. But if you see a leaf suddenly veer sideways or speed up, you know a hidden current, a whirlpool or a rock is pulling it off course. Peculiar velocities are those sideways veers. To measure them, scientists first calculate how fast a galaxy should be moving based purely on its distance and the universe's expansion rate. Then they use other methods, like measuring the brightness of certain stars within the galaxy, to get its true distance. The difference between the predicted speed and the observed speed is the peculiar velocity, the fingerprint of local gravity's tug. This is how the original Seven Samurai team detected our race toward Centaurus. They saw that our motion and the motion of our neighbors was far too fast to be explained by expansion alone. We were all veering off the Hubble flow, caught in a hidden current, but to see the shape of that current, to map the gravitational valleys in 3 dimensions, astronomers had to confront a strange illusion in their data, a phenomenon with a technical name that hides a beautiful insight. When we map the universe using redshift, we are not looking at a perfect snapshot. Redshift tells us how fast something is moving away from us, but that motion is a combination of the smooth Hubble expansion and the messy, local peculiar velocities. This creates a distortion in our maps known as a redshift space distortion. In regions of immense gravity, like the core of the Great Attractor, galaxies are not just expanding away, they are also falling inward toward the center of mass. From our distant viewpoint, this infall motion makes them appear squashed together in the redshift map. Imagine a dense crowd all running toward a single point on the far side of a field. From your seat on the opposite side, the people in the middle of that crowd, those falling directly toward the point, have very little sideways motion relative to your line of sight. Their motion is mostly toward or away from you. This makes them appear tightly packed in your view, compressed along your line of sight. That is the squashing effect known as the Kaiser effect. It makes the dense nodes of the cosmic web, the attractors, look even denser and more elongated in our redshift maps than they truly are in real space. Conversely, in the vast voids where galaxies are being pushed outward by the growth of emptiness, they appear stretched out and dispersed in the redshift view. These distortions are not mistakes, they are gold mines. By carefully analyzing how galaxy clusters appear squashed and how voids appear stretched in redshift surveys, cosmologists can reverse engineer the strength and direction of the gravitational flows. They can measure the rate at which galaxies are falling into the Great Attractor, which in turn tells them the total mass of the attractor itself, both visible and dark. This technique transforms a static map of galaxy positions into a dynamic movie of cosmic motion. It allows us to see the universe not as a frozen sculpture, but as a living, flowing entity, with rivers of galaxies streaming down slopes of dark matter toward hidden basins of gravity. The squashed signature in the direction of Centaurus is one of the clearest dynamic proofs we have that the monster's pull is real, ongoing, and shaping our corner of the cosmos in real time. The lightest particles in the universe may hold the key to its largest structures. Among the countless particles streaming through space, neutrinos are the most elusive, passing through entire planets as if they were empty air. For decades, they were thought to be massless, ghostly spectators in the cosmic drama. but we now know they possess a tiny, almost imperceptible amount of mass. This minute mass changes everything about how we model the growth of the cosmic web. Because neutrinos are so light and interact so weakly, they travel at nearly the speed of light for most of the universe's history. They do not clump together under gravity like dark matter or ordinary matter. Instead, they stream freely, a vast hot wind blowing through the scaffolding of the cosmos. This streaming has a smoothing effect. Think of trying to build a sandcastle while a gentle, persistent breeze blows across the beach. The breeze does not stop you from building altogether, but it makes it harder to form the finest, sharpest details. It rounds off the peaks and fills in the tiniest crevices. In the universe, neutrinos are that cosmic breeze. Their high velocity and reluctance to cluster mean they wash over the densest regions of dark matter, suppressing the growth of structure on the smallest scales. They do not prevent giant clusters from forming, but they subtly alter the timeline and the final distribution of matter. For a structure like the Great Attractor, this neutrino influence is written into its very foundation. The immense node where dark matter filaments converge would have begun as a slight overdensity in the early universe. As gravity worked to amplify that overdensity, pulling in more dark matter and gas, the sea of streaming neutrinos provided a countervailing pressure. They carried energy and momentum away from the densest spots, slowing down the collapse just enough to leave a statistical signature in the way galaxies are clustered around the attractor's core. The effect is incredibly subtle, a fingerprint on the cosmic web that requires mapping millions of galaxies to detect, but it is a crucial piece of the puzzle. When cosmologists run their supercomputer simulations of the universe, they must include the mass of neutrinos to get the large-scale structure to match what we actually observe. Without them, the models predict too many small galaxy groups and a slightly different clustering pattern around massive nodes. The presence of massive neutrinos helps explain why the cosmic web looks the way it does, with its vast filaments and grand nodes, rather than an even finer, more tangled mesh. So the ghostly neutrino, a particle that can pass through light years of lead without a single collision, has been quietly shaping the architecture of superclusters for billions of years, its faint whisper leaving an imprint on the gravity wells that pull entire galaxies. Gravity might not be the force we think it is. For a small but vocal group of physicists, the entire framework of dark matter and hidden attractors is an elaborate solution to a problem that does not exist. They propose a radically different answer, that our theory of gravity itself is incomplete, especially in the weak, sprawling fields that govern galaxies and superclusters. This idea, known as modified Newtonian dynamics, or MOND, suggests that Isaac Newton's famous law needs a slight adjustment in environments where gravity is extraordinarily faint. In the outer reaches of galaxies, where stars orbit at speeds that should send them flying into the void, MOND adds a tiny extra term to the equations, a correction that perfectly predicts those high velocities without invoking any invisible matter. For its proponents, the Great Attractor is not proof of a dark matter node, but evidence of a cosmic scale failure in Einstein's general relativity. They argue that the coordinated flows of galaxies, the bulk motions toward Shapley, and even the deep wells of the cosmic web could emerge naturally from a modified law of gravity, one that behaves differently over millions of light years than it does in our solar system. It is an elegant, minimalist idea, cutting out the need for an entire unseen universe of particles. Why invent dark matter, they ask, if you can simply rewrite the textbook? The arguments against this view, however, are formidable and rooted in direct observation. While MOND can explain the rotation of individual galaxies with startling success, it struggles catastrophically with the largest scales. The Bullet Cluster provides the most famous counter-evidence. This is a system of two galaxy clusters that have violently collided. observations show that the hottest, most massive gas, the normal matter, was slowed by the collision and sits in the middle. But the gravitational lensing map, which shows where the majority of mass actually is, reveals two distinct peaks far outside the gas, where the dark matter from each cluster sailed through the collision unaffected. This is a direct image of dark matter separating from normal matter, something modified gravity cannot easily explain because gravity should follow the mass you can see. On the scale of the Great Attractor and the cosmic web, the challenges multiply. Supercomputer simulations that start with the observed conditions of the early universe and run solely on the rules of general relativity and dark matter reproduce the filamentary web, the great walls, and the massive nodes with stunning accuracy. Simulations using modified gravity theories have so far failed to build such a rich, detailed cosmic structure from the primordial soup. They do not naturally create the intricate, clustered tapestry we observe. Furthermore, the precise patterns in the cosmic microwave background, the ancient light from the Big Bang, match predictions based on dark matter cosmology to an extraordinary degree. These patterns are a fingerprint of the universe's infant structure, and they align with a model where dark matter's gravity provided the initial scaffolding. For the vast majority of cosmologists, this interconnected web of evidence, from colliding clusters to the infant universe to the successful simulations of large-scale structure, forms a coherent picture that is simply too powerful to discard. The dark matter model, for all its mystery, provides a single, unifying framework that works from the smallest dwarf galaxies to the largest superclusters. The Great Attractor, in this view, is not a flaw in our gravity, but a triumphant prediction of it, a signpost pointing toward the invisible architecture that truly holds the universe together. Yet the persistence of modified gravity theories serves a vital purpose. It keeps science honest, constantly testing its foundational assumptions against the hard light of data. The next generation of eyes are already turning toward the dark. Our current maps of the cosmic web, for all their grandeur, are still sketches compared to the masterpiece we know is out there. To move from inference to precision, from shadow to substance, we need a new kind of census, one that will count not thousands or millions, but billions of galaxies. This is the promise of the observatories now being built and launched, instruments designed not just to see farther, but to see everything. The European Space Agency's Euclid spacecraft is a pathfinder in this new era. Its mission is not to study individual stars or planets, but to survey the geometry of the dark universe itself. Flying 1,000,000 miles from Earth, Euclid will spend years imaging over a third of the entire sky in both visible and infrared light, cataloging the shapes and positions of an estimated 2 billion galaxies. Its primary tool for weighing the unseen is weak gravitational lensing. This subtle effect occurs when the gravity of dark matter filaments and clusters warps the fabric of spacetime, bending the light from galaxies behind them. Euclid will measure the infinitesimal distortions in the shapes of those distant background galaxies, distortions so slight they are statistically invisible in any single image. But across 2 billion galaxies, a pattern emerges. By analyzing how these shapes are systematically stretched and aligned, scientists can create a three-dimensional mass map of the cosmic web, charting the distribution of dark matter with a fidelity we have never before achieved. For the Great Attractor, this means we will no longer have to guess at the shape of its dark matter skeleton. Euclid will trace its filaments in vivid detail, showing exactly how they converge on the Norma Cluster and how they connect to the wider Laniakea structure. It will weigh the attractor's total mass, dark and visible, with a precision that could finally close the book on the missing baryon problem, revealing if the warm-hot intergalactic medium truly fills the cosmic arteries as predicted. Following close behind is NAS, a Nancy Grace Roman Space Telescope, named for the pioneering astronomer who paved the way for Hubble. Roman shares Euclid's wide-field ambition but brings a different set of tools to the cosmic cartography table. Its core cosmology survey will peer even deeper into the infrared, capturing the light from galaxies whose visible glow has been stretched by the universe's expansion over billions of years. Roman's immense field of view, 100 times larger than Hubble's, will allow it to perform a galactic census of staggering speed and depth. One of its key goals is to measure baryon acoustic oscillations, those frozen sound waves from the early universe, with exquisite accuracy across a vast volume of space. By mapping the preferred 500 million light-year separation between galaxies across different cosmic epochs, Roman will act as a forensic investigator of dark energy, measuring how the expansion rate of the universe has changed over time. This directly impacts our understanding of structures like the Great Attractor. By pinning down the expansion history, we can better isolate and measure the peculiar velocities of galaxies, disentangling the local pull of the attractor from the global flow of the cosmos. Roman's data will refine our maps of bulk flows, telling us with new certainty how much of our motion is due to Shapley, how much to the attractor, and whether even larger currents are still hidden in the data. On the ground, a colossal new eye is rising in Chile, the Vera C. Rubin Observatory's legacy survey of space and time, the LSST, will take wide-field astronomy to a breathtaking extreme. Using the largest digital camera ever built, it will scan the entire southern sky every few nights for a decade, creating a motion picture of the universe. This relentless survey will detect tens of billions of galaxies and track millions of transient events, from supernova to asteroid movements. For the study of large-scale structure, the LSST power is in its dynamic range and its time domain coverage. It will find dwarf galaxies and faint streams of stars that are exquisite traces of dark matter halos, revealing the fine structure within the great filaments. Its repeated observations will allow scientists to measure the proper motions of galaxies within our local universe with unprecedented accuracy, adding a crucial new vector to our understanding of galactic flows. Watching how galaxies move sideways in the sky, not just toward or away from us, will provide a full three-dimensional velocity map of our cosmic neighborhood. This will let us see, in effect, the swirling eddies and currents within the river flowing toward the Great Attractor, revealing substructure and mergers within Laniakea that are invisible to our current static maps. Together, these missions represent a qualitative leap. They are not merely bigger telescopes, they are engines of statistics designed to overcome cosmic variance by sheer volume of data. Where we once inferred the web from a sparse sampling of bright galaxies, we will soon drown in an ocean of points, each one a marker in the dark matter landscape. The Great Attractor will cease to be a mysterious anomaly measured by its indirect effects. It will become a precisely surveyed feature, its mass known to within a few percent, its gravitational influence mapped from its dense core out to the furthest tendrils of its influence. We will see if the Vela Supercluster is truly part of its complex, and we will watch in real data as the flows from the dipole repeller push against the pulls from Shapley. These missions will test the limits of the cosmological principle by mapping billions of galaxies and asking if the distribution is truly smooth, or if the Great Walls hint at a more textured reality. They will weigh neutrinos by their subtle suppression of small-scale structure and constrain the nature of dark energy by how it has shaped the web over time. In just a few years, the hidden architecture that has taken decades to glimpse will be rendered in high definition, and the final secrets of the attractor that pulls us will be brought into the light. The final secret is not about the cosmos, but about us. For centuries, humanity grappled with the idea that Earth was the center of the universe, a notion dismantled first by the Sun, then by the galaxy. Yet a subtler, more profound centrality persisted, the quiet assumption that our place in the cosmos was at least somehow typical, somehow stationary. The Great Attractor shatters even that last comforting illusion. We are not merely off-center, we are in motion, caught in a current that defines our very existence. Our galaxy, with its hundreds of billions of stars, is not a fixed landmark. It is a leaf in a river, and we are riding along on its surface, unaware of the current except through the subtle shift of distant landmarks. That 600 km/s rush is not an abstract measurement. It is our true velocity through the fabric of space, a speed so immense it would take us from Earth to the Moon in under 11 minutes. And we are not moving toward something brilliant and commanding. We are falling toward a place of profound darkness, a gravitational focal point hidden behind the glittering debris of our own galactic backyard. The center of our local universe is a place we cannot look upon directly, a monster we must map by the shadows it casts and the trails it leaves in the motions of others. This journey strips us of any lingering cosmic privilege. We are not at the heart of anything. We are out on the sparse, distant fringe of a supercluster, far from the bustling core, following a current set in motion billions of years before our sun even ignited. And the ultimate destination, the Great Attractor itself, is no final resting place. It too is adrift, a massive whirlpool within a greater river, flowing toward the even more immense Shapley Supercluster. We are passengers on a journey within a journey, caught in a hierarchy of motion that stretches beyond our sight. There is no special location, no still point in the turning universe. Every galaxy, every supercluster is in motion relative to something else, bound by gravity's chain into an endless dance where to be is to move. This realization is the true culmination of the mystery. The Great Attractor is not just a hidden structure, it is a mirror. It shows us our place not as central observers, but as participants in a story far grander than our own. A story written in gravity, dark matter, and flowing light, where we are both the audience and a tiny, moving part of the spectacle. The monster pulling us is not a place, but an event. The Great Attractor is a verb, not a noun. It is the name we give to the ongoing, billion-year process of gravitational collapse at the heart of our local universe. Think of a waterfall frozen in a single photograph. You can see the water's motion, the spray, the powerful plunge, but the image itself is static. The Great Attractor is that photograph. We are seeing a single frame in a movie that has been playing for over 13 billion years. The frame where our galaxy happens to be part of the flow. This process began with the faintest whisper, a quantum fluctuation in the dark matter moments after the Big Bang, a region that was just a fraction of a percent denser than its surroundings. Over eons, that tiny overdensity acted like a seed. Gravity, patient and relentless, pulled more dark matter toward it. That dark matter scaffold then guided ordinary gas into its growing wells, where it cooled, fragmented, and ignited into the first galaxies. Those galaxies did not just appear near each other, they were born along the invisible filaments of this emerging structure, destined from the beginning to flow together. The attractor is the moment in that story when the separate streams begin to merge into a single, roaring river. Right now, we are witnessing the intermediate stage. The filaments of Laniakea are still distinct rivers of galaxies, like separate tributaries feeding a great lake. The Norma Cluster is the dense, churning center where those currents are beginning to violently interact, where galaxies are being stripped of their gas and hurled into new orbits. But the process is far from complete. Most of Laniakea's 100,000 galaxies are still in transit, still flowing along their filamentary highways toward the core. We are in the era of gathering, not the era of consolidation. This dynamic view changes everything about what the Great Attractor means. Its immense gravity is not a mysterious external force. It is simply the collective weight of all that infalling material, the consequence of a universe that has been patiently organizing itself since the beginning of time. The attraction is the universe finishing a piece of its own construction, and like any construction site, it is a place of both creation and destruction. As galaxies fall into the deepening well, they are torn apart by tidal forces. their stars scattered into a diffuse halo that will eventually form the smooth background of a future giant elliptical galaxy. Their gas collides, heats to millions of degrees, and glows in X-rays, painting the intracluster medium we now detect. This makes the attractor a cosmic crucible, recycling the raw materials of stars and planets on a scale so vast it defies human analogy. It is the engine of transformation for our entire local cosmos. This process ties directly to the life cycle of the cosmic web itself. The web is not a permanent sculpture. It is a living, breathing entity with matter constantly flowing from the voids along the filaments and into the nodes. The Great Attractor is one of those nodes, a major hub in the cosmic transportation network. For a time, these nodes grow brighter and more massive as they feast on the infalling material. But the web is also evolving. Over time, as the densest nodes pull in everything from their immediate filaments, those filaments may thin and eventually sever, cutting off the supply. The node's growth slows. Furthermore, the accelerating expansion of the universe, driven by dark energy, acts on the largest scales. Over trillions of years, it will stretch the web itself, pulling filaments apart and isolating the great nodes like lonely islands in an ever-darkening sea. So the Great Attractor captures a specific, precious phase in cosmic history. It is the phase of peak assembly, after the initial chaos of the Big Bang has settled into clear patterns, but before the long, slow isolation dictated by dark energy truly begins. We are living in the golden age of structure formation, and the pull we feel is the signature of that golden age. It is the universe actively building its largest creations, and we have a front row seat to the construction. This means the ultimate secret of the Great Attractor is about time. It is a clock whose hands are galaxies, ticking toward a future where our local universe will be unrecognizable, and a reminder that we are not just passing through space, but through the profound and ongoing story of creation itself. These colossal patterns in the dark are not random. The sprawling filaments, the immense walls, and the haunting voids we have mapped are more than just scenery. They are the fossilized imprints of the universe's first moments. The cosmic web is a direct descendant of the Big Bang, a living relic that allows us to perform archaeology on creation itself. The story begins not with a bang, but with a whisper, a quantum whisper. In the unimaginably dense, hot soup of the universe's first fraction of a second, empty space itself was not empty. It was a seething quantum foam where particles and energy flickered in and out of existence. Within that chaos, tiny fluctuations in density were inevitable. Some regions were a minuscule amount denser, others a minuscule amount emptier than the average. These were quantum ripples on a scale smaller than a single atom. Then, in an event called cosmic inflation, the universe underwent a period of exponential expansion, doubling in size over and over again in a fleeting instant. This inflation did not smooth out those quantum ripples, it stretched them. It took those subatomic wrinkles and blew them up to sizes spanning light years, then millions of light years, imprinting them across the entire observable cosmos. Think of blowing up a balloon with a faint, microscopic texture on its rubber. As the balloon inflates to the size of a house, that tiny texture becomes a giant, landscape-scale pattern you can see from across the room. Inflation did exactly that to the infant universe. Those stretched quantum ripples became the blueprints for all future structure. The slightly denser regions held a tiny gravitational advantage. Over the next 13.8 billion years, gravity got to work, relentlessly amplifying those blueprints. More matter was drawn into the overdense regions, which grew into protogalactic clouds, then galaxies, then clusters. The underdense regions were drained, becoming the vast voids we see today. This means the specific pattern of the Great Attractor, the Sloan Great Wall, and the Boötes Void was not predetermined, but it was probabilistically seeded by those random quantum ticks. When we map the distribution of galaxies in projects like the Sloan Digital Sky Survey, we are not just making a map of where things are now. we are developing a photograph of those primordial quantum fluctuations, a snapshot of the universe's quantum mechanical birth certificate, enlarged to a scale of billions of light years. By studying the statistical properties of the cosmic web, the spacing of clusters, the sizes of voids, cosmologists can work backwards. They can infer the exact nature of those initial ripples, testing theories about inflation and the fundamental forces that govern the universe's first fleeting instants. The Great Attractor, therefore, is more than a gravitational pit. It is a direct messenger from a time before time, a cosmic monument built upon a foundation of quantum noise. This ultimate map is already being drawn, not on paper, but in the silent language of data gathered by the next generation of cosmic observatories. The goal is breathtakingly simple in concept and staggeringly complex in execution, to create a complete three-dimensional atlas of the observable universe. This will not be a map of highlights, but a full census plotting the positions and motions of billions of galaxies, revealing the cosmic web in its entirety for the very first time. Projects like the Dark Energy Spectroscopic Instrument, known as DESI, are leading this charge. Mounted on a telescope in Arizona, DESI is not a camera, but a robotic eye with 5,000 tiny, precise fibers. Each night, it can point these fibers at 5,000 individual galaxies or quasars, capturing their light and splitting it into spectra to measure their exact distance. Over 5 years, it aims to catalog over 35 million galaxies, constructing a three-dimensional volume of the universe stretching back 11 billion years. This map will be so vast and detailed that the Great Attractor will shrink from a mysterious focal point to a single, well-measured feature within a sprawling continent of data. We will see its filaments not as inferred rivers, but as clearly defined highways, traced by millions of individual galactic points of light, showing exactly how our local group connects to the Norma Cluster and beyond. This three-dimensional context is crucial because it strips away the illusion of two dimensions. In a flat sky map, structures can appear connected when they are actually at vastly different distances, creating false walls and mirages. The ultimate three-dimensional map will settle debates about the true scale of the largest structures, telling us definitively if the Hercules Corona Borealis Great Wall is a single, connected filament or a chance alignment of separate threads. It will show us the true architecture of the Pisces Cetus Supercluster complex, revealing whether it is a unified structure or a looser association. For the Great Attractor, this means we will finally see the full extent of its gravitational influence. We will be able to trace the boundaries of the Laniakea supercluster with absolute precision, identifying every galaxy that is flowing toward its basin, and just as importantly, those that are not, belonging to a neighboring watershed. This will allow cosmologists to perform a perfect mass accounting, weighing the attractor by summing everything within its gravitational domain and comparing it to the observed motions of galaxies, providing the most stringent test yet for our models of dark matter and gravity. But the ambition goes even deeper than a static snapshot. By mapping galaxies at different distances, which equates to different look-back times, these surveys will create a kind of cosmic time lapse. We will see the cosmic web as it was billions of years ago in the distant slices, and as it is today in the nearer slices. This will let us watch the Great Attractor itself in the process of formation. We will see how its filaments thickened over time, how galaxies began to stream along them, and how the central node grew in density. It transforms the attractor from a contemporary mystery into a historical document, a chapter in the biography of structure formation that we can read from beginning to middle, with our present position as just one page. The ultimate promise of this complete map, however, is the discovery of patterns we cannot yet conceive. When you have a complete census, you can ask new kinds of questions. Are there symmetries in the web, repeating motifs on the largest scales? Does the distribution of voids follow a predictable pattern? Is there an upper limit to the size of a structure, a true end of greatness, or does the hierarchy continue? Finding an answer to any of these would rewrite our textbooks. This comprehensive view might even reveal the gravitational signature of structures so immense they make Shapley look modest. Patterns woven into the universe so large we are only now building tools wide enough to see them. In this future map, our journey toward the hidden monster will be rendered as a single, elegant flow line among billions, a testament to the fact that to understand our place, we must first chart the entire continent in which we reside. Our journey began with a simple, unsettling fact, a speed we could not explain. It ends not with a single answer, but with a transformed vision of reality. The Great Attractor is no longer a hidden monster in the dark. It is the beating heart of our home continent, a dynamic node where the rivers of the cosmic web converge. Its immense pull, once a baffling anomaly, is the natural consequence of gravity patiently assembling an entire supercluster over 13 billion years. This story has taken us from the first whispers of quantum fluctuations to the fiery glow of intergalactic gas, from the ghostly influence of dark matter to the silent push of immense voids. We have seen that to understand this one gravitational pit is to grasp the architecture of the universe itself. The secrets of the Great Attractor are, in truth, the keys to our cosmic fate. They help us weigh the invisible dark matter that sculpts all structure, measure the repulsive dark energy that will one day tear it apart, and trace the delicate balance between gravity's relentless pull and the universe's accelerating expansion. Every galaxy's peculiar velocity, every vast wall, every haunting void is a piece of this grand puzzle. We are not passive observers of a static cosmos. We are participants in an ongoing construction project of unimaginable scale, living inside a mystery that is still unfolding. So as you look up at the night sky, remember the current you cannot feel. We are all flowing, caught in a grand and ancient river, moving toward a hidden heart. Which of these 30 secrets shifted your perspective the most? Was it the realization that we are racing toward a place we cannot see, or that most of the universe's matter is completely invisible? Share the idea that amazed you in the comments below and keep wondering.